So we discussed a few things on the whiteboard in the last class. So let me take you through the lecture slides just to refresh that knowledge. And in the meanwhile, the class length would be almost uh, uh, almost equal to the number of the students which are in the class. At the moment, we have got only, I think, 9 attendees. So let me recap what we discussed in the last class. So in the last class, we started convection. So up till now, we discussed only conduction. So now this is chapter number 6 of Sanchez book. So we know that if we want to calculate the convection heat transfer, we have got this formula, which is shown on this lecture slide, which is Newton's law of cooling. And so the convection flux is equal to H into Ts minus T infinity. So as we discussed that here in convection, the major challenge is to calculate the value of H. And now H is flow property as well as fluid property, and it also depends upon the geometry on which the flow is happening, whether it is internal flow or whether it is external flow, or there is surface roughness on the solid surface. So it means that we need to cater for different things. So H cannot be tabulated in a table for any given fluid, because the it depends upon the velocity as well as the nature of the flow. So it means that we need to solve some equations for that. So first of all, the first concept which I told you, that was the no slip condition, that a fluid in motion comes to a complete rest at the surface and assumes the same velocity which is of that surface. So if that surface is stationary, the first layer of the molecule would have zero velocity. Otherwise, if it is moving like some aeroplane or some object, then the first layer of the molecule would have the same velocity as that of that object. So the no slip condition is responsible for the development of the velocity boundary layer. So I discussed about the velocity profile in the last class. I shown you in terms of molecular development of the boundary layer, that the first molecule, because it is at rest, it has got the same velocity as this stationary surface. Then what will it do, that it would apply a drag force on the next layer. So that's why the velocity would be a little bit less than the free stream velocity. Then the second layer of molecule would apply a drag force on the third layer, and that drag force is directly proportional to the viscosity of the fluid. So more the viscosity, more the drag force, and this velocity profile would take longer to reach the free stream value, which is here. It is shown here. So here the black line, this is the velocity profile which is being developed in the boundary layer region. So how do we define boundary layer region? That would come on the next slide. So first of all, if we apply the energy balance here, then on the first layer of molecules, so because at the first layer that is stationary, so the heat would be transferred from the solid surface to the first layer by Q conduction, and then from the first layer to the second layer, because the second layer molecules are moving, so there would be convection. So Q conduction would be equal to Q convection. So if we apply the balance on the first layer of molecule, then we can get minus K of fluid into partial T by partial Y at Y is equal to 0. Y is equal to 0 is the Y location at this surface, and then Q convection, that is equal to H into Ts minus T infinity. So from here we can calculate H is equal to minus K fluid partial T by partial Y at Y is equal to 0, Ts minus T infinity. Now if you look closely at this relation, K of fluid, that is a fluid property, we can determine it easily from any table, so that is fine. Ts is the temperature of this surface, which can be determined by some thermostat, and then T infinity is the temperature of the surrounding fluid which is flowing over this solid surface. So that can also be calculated or measured by using some device. So it means that the only thing which is not known to us in this relation is this gradient partial t by partial y at y is equal to 0. So in order to get to that partial t by partial y, we need to know the temperature field in this boundary layer. So that's why, and in order to get the temperature field, first of all, we need to know the velocity distribution inside the boundary layer. So that's why we have to solve for Navier-Stokes equations first, and then the convection equation to get to the this temperature distribution. So in for you guys, it is a little bit out of order at this moment because we are studying fluid mechanics too at the same time as the heat mass transfer course. So usually this heat mass transfer course comes in the next semester when you study the fluid mechanics course. So in that you discuss about the internal and external flows in detail and all those fluid flow phenomena. So, but I would explain a little bit about the Navier-Stokes equation and things like that, but not in great depth because that you are going to study in your FM2 course. So now here on this slide we can see that if we want to calculate the total heat transfer from a surface, then we need to take integral for the local heat flux. So it means that local heat flux, if we write that Ts minus T infinity H into dAs. So it means that on this surface H value is changing with the location. Why is that? Because partial T by partial Y at Y is equal to 0, that changes at every point due to development of boundary layer. So so in order to get to the in order to apply this formula, we need to use an average value of h. So average value of h can be calculated by this formula given here. So this h bar is the value you have been given up till now. In all the conduction chapters, when we say that h value is 20 watt per meter square Kelvin, 100 watt per meter square Kelvin, so we were talking about this h bar basically. So it means that this is the average value of h, which would give us the same convection heat transfer, which we would be getting by this integral formula, right? So I hope that this point is clear that what is the significance of this h bar. This is the average convection coefficient. So now if we talk about the boundary layer growth, now you can easily see that here we have got a free stream velocity of u infinity, but when it comes into the boundary layer region, because the first layer of molecules which is attached with the solid surface, that is at zero velocity. So it would put a drag force on the second layer of molecules. So the consequence of that is the velocity of that layer would be very less, and that drag force will decrease as we move away from the wall. So it means that as a result of that, the velocity would increase, and at some point it would be equal to the free stream velocity. So that point where the free stream velocity 99% of the free stream velocity is achieved, that is called boundary layer thickness, and that is represented by delta. Here you can see delta, and it is showing you the distance between the solid surface and the edge of the boundary layer. So edge of the boundary layer, how do we define it? That is that is the distance away from the wall at which the free stream velocity becomes equal to the molecular velocity becomes equal to the 99% of the free stream velocity. So that is written here. U of y becomes equal to
सर ये
0.99.
दोबारा एक्सप्लेन कर दें, ये दोबारा
Yes.
एक्सप्लेन कर दें।
बेटा
फ्री वेलोसिटी वाला
yes.
सर दोबारा,
जी
डेल्टा
फ्री स्टीम
डेल्टा।
बिल्कुल जी, मैं दोबारा एक्सप्लेन कर देता हूँ यहाँ पे। इफ वी कैन सी दैट हियर वी हैव गॉट u infinity which is free stream velocity, and when because if we say that this was just for example it is 10 meter per second. So when the first layer here becomes in contact with this solid surface, the molecules of the first layer would have zero velocity. So it means that it would apply a drag force on the second layer. So it means consequently the second layer molecules would have very low velocity, maybe zero point 0.5 meter per second, and then the third layer would have 1 meter per second, then 5 meter per second, 8 meter per second, and then here at this point, at certain point away from the wall, right, at certain distance away from the wall in the y direction, the the molecular velocity would become equal to 9.9 meter per second, which is basically 0.99 of the free stream velocity. So that thickness, when that the velocity of the molecules become equal to 0.99% of the free stream velocity, that distance or thickness is called boundary layer thickness, and that is shown by delta. And you can see this black line that it is growing in x. It means that the influence of this boundary layer region or the viscous effect, they propagate away from the wall. So that's why this boundary layer grow. It means that at this point, if we talk about the edge of the boundary layer here on the right hand side, at this point the velocity of the molecules would become equal to 9.99 meter per second. But if we talk about this point, at so here the boundary layer thickness is very less. So it means that at this point the molecule velocity would become equal to 9.9 meter per second. I hope Atif that it answers your query.
सर
So
ये चेंज, सर ये चेंज क्यों हो रही है थिकनेस सर, इसको थोड़ा सा एक्सप्लेन कर दें।
बिल्कुल जी, देखे ना, इफ यू go along a molecular layer, Atif, if a molecule which is here, so the velocity is 10 meter per second. So at this point in the beginning, because the force which would be exerted on it, that would have been only on this area, only on this is small distance. But if you keep on dragging that molecule, then what will happen, that the molecular velocity would decrease as it moves along x.
और
Do
सर
you
गॉट इट सर।
understand that?
यस सर।
So that's why this thing grows in y, because now the more molecules would have less velocity, because as we move along x, the drag force would continue to happen. So that's why the velocity in a stream line would decrease in the boundary layer, and that's why the boundary layer would grow in x. Okay. So the region which is in the inside region, that is called viscous region, or we can also call it boundary layer region. And the outer region where we have got free stream velocity, that is called outer region, right? And then these are the formulas. One you must have studied in FM1 in chapter number 1, which is when you were discussing about Newtonian fluids and non-Newtonian fluids, that the shear stress is equal to mu into partial u by partial y, and this second formula, that is coefficient of friction, that you would come across that when you would be discussing the external flows in your FM2. I think this is chapter number 8 in your Munson's book. So you would come across this formula. CF is equal to T of S divided by half rho u infinity square. ठीक है? So CF is the main parameter which would determine that how much drag force is exerted uh, on a solid surface by some molecule. So So that is the main parameter for the calculation of friction on friction factor for this flow. So you would discuss in detail in FM2. So now coming towards the thermal boundary layer. So similarly, as we discussed for the velocity boundary layer, we would have thermal boundary layer here. So let's suppose that we are talking about the cooling of this surface. So it means that now we have got the maximum temperature at this surface. So now we are trying to cool it with the flow of cold fluid over it. So now you can see that the first layer of the molecule that has got the same temperature which would be of this surface, which is Ts. Here Ts is shown. Now that temperature would decrease to the free steam temperature, which is T infinity in this case. So it means that now this red line, which is shown here, that is the temperature profile. So it tells you that the temperature of the molecule decreases from the surface temperature Ts to the T infinity, which is the free steam temperature. So, in order to define the thermal boundary layer, which is denoted by delta T here, that is that we say that this ratio of the temperature difference Ts minus T. Here T is the temperature of T is a function of Y. This second term in the numerator, that is this profile, it is showing you this profile T of y. Basically it should be T of y. T is function of y, this second term on the numerator, and then in the denominator it is Ts minus T infinity. Ts is the surface temperature and T infinity is the free steam temperature. So when this ratio becomes equal to 0.99, then we can say that that distance is the thermal boundary layer, right? So as we discussed the velocity boundary layer, or precisely we call it hydrodynamic boundary layer. So in the similar terms, we can define the thermal boundary layer. And then for that, Qs is equal to minus Kf into partial T by partial y at y is equal to 0 for the first molecular layer. And then from there we can calculate H, which we already did in the previous slide, which is H is equal to minus Kf into partial T by partial y at y is equal to 0. So here partial T by partial y at y is equal to 0, that is the major challenge to be which we want to calculate this term, this gradient term. But in order to get this term, we need to know that what is the temperature at the wall, and then what is the temperature inside the boundary layer. So it means that we need to solve boundary layer equations for this. But in order to solve temperature equation, first of all, we need to solve velocity boundary layer equations, because first we get to know the velocity there, then only then we can calculate the temperature. While that, I would tell you maybe in 15 minutes time, and we would do that derivation or show those equation on the whiteboard. So just take it as this, that in order to determine partial T by partial y at y is equal to 0, we need to know temperature. And in order to get the temperature field inside the boundary layer, we need to determine first of all the velocity inside the this boundary layer. And for that we need to solve boundary layer equation. So how do we get to the boundary layer equations from the Navier-Stokes equation? That I would explain maybe in 15 minutes time on the whiteboard. This is just the revision which we discussed in the last class. So it is first of all there are three parameters I discussed. Reynolds number. We all know that Reynolds number is the ratio of inertial to viscous forces, and there is a critical Reynolds number below which the flow becomes laminar, and beyond that the flow transition to turbulence starts. For the pipe flow, that value is 2200. For the boundary layer flow over a flat plate, that value is 5 lakh or half million. So because in that case, the definition of Reynolds number is different for the internal flow as well as for the external flow. In the internal flow, we have got characteristic length as diameter, and for the external flow, because there is no diameter, then we take the distance from the leading edge of the flat plate as the characteristic length. So that is the difference. And then in the velocity, in the pipe flow, we have got mean velocity, and for the external flow, we have got free stream velocity, which is u infinity. Okay, ji. So then we discussed that we can non-dimensionalize h by using HLC upon k. So we can readily see that it is the same formula as we use for the Biot number in chapter number 5. The only difference here is this k is for the fluid, but for the Biot number it was basically the k for the solid material. So here it is for the fluid. Now, in order to quantify it, as I told you in the last class, maybe you don't remember that it is the ratio of convection heat transfer to the conduction heat transfer in that fluid. So it means that Nusselt number is basically the ratio of conduction heat transfer to the convection heat transfer in the fluid to the conduction heat transfer in the fluid. Okay, now tell me one thing. Is there any possibility that there is only conduction within the fluid, no convection? Because that is the case when Nusselt number would be equal to 1. ठीक है ना? When Q conduction is equal to Q convection, is there any possibility that we can have that problem, that where there is no uh, convection? Convection means bulk motion of fluid. Anyone?
सर सरफेस पे
नहीं, ये कोई ऐसा फिनोमेना हो सकता है जिसके अंदर हमारी बल्क मोशन ना हो रही हो फ्लूइड में? अच्छा, let me explain it a little bit to you. Maybe in couple of minutes. It would take couple of minutes. If we put water in a kettle, ठीक है, किसी भी हम केटल में पानी डालें और उसको नीचे से गर्म करना शुरू कर दें बाय बाय इलेक्ट्रिक स्टोव या फिर गैस स्टोव से, क्या होता है उसमें? ये होता है कि वो पानी गर्म होता है, और जो गर्म पानी होता है ड्यू टू buoyancy effects it rises towards the top of the that water layer. ठीक है, and after some time when it is heated enough you can also see the bubbles going upward. ठीक है, so before that, so it means that due to change in density of the fluid, the flow moves up. So that is the natural convection. ठीक है, now is there any way, now if I reverse it, now if I put the kettle, the same kettle, and give heat from the top, what will happen? That the heat would flow from the top surface to the bottom surface. Now, but the problem is, now the scenario is that the top surface would have been the most light molecules, because they are the most heated molecules. Now they cannot go downwards, right? They would stay upwards. At the first layer would stay at the same top position, because that is the most heated, most hot molecules, and they cannot go above, because at the above we have got some restriction. So it means that they would only transfer heat to the bottom layer by conduction. So there would not be any fluid motion due to that buoyancy effect. Is that clear? Now that phenomena is called stratification. 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 Okay? In which the fluid transfer heats only by molecular collisions. So it cannot travel due to the fact that the lighter molecules are at the top, so they cannot move downward. So I hope that this point is clear. So only in case of stratification, Nusselt number would be equal to 1. Otherwise, in all other heat transfer phenomena, Nusselt number always be greater than 1. So that is first thing you need to know. So Nusselt number represents enhancement of heat transfer through a fluid layer as a result of convection. Convection means bulk motion of the fluid relative to the conduction. Conduction means the heat transfer due to molecular collisions. So that is the conduction here, which is also called diffusion, and convection is the bulk motion of the fluid. Okay? So large the Nusselt number, the more effective the convection. It means that the more bulk motion is happening, which is taking the hot molecules away from that region to the area where there are cold molecules. So in that case, the heat transfer would be more vigorous. So Nusselt number equal to 1 means प्योर कंडक्शन इनसाइड दैट फ्लूइड, और उसकी एग्जांपल मैंने आपको बता दी है, stratification in which we give heat to a fluid from the top. So the top layer of molecules, they are at the highest temperature and they cannot go downwards because they are the lightest one. So they would be giving heat to the lower layer of molecules only by molecular collision. So that is the Nusselt number. And then Prandtl number is the ratio of the relative thickness of the velocity and the thermal boundary layer. And I discussed that for Prandtl number 1, delta delta T is less than delta H. Delta H is the hydrodynamic thickness, and delta T is the thermal boundary layer. So that formula is mu upon alpha, mu Cp upon K, and this is the ratio of molecular diffusivity of momentum to the molecular diffusivity of heat. Now, up till now, this is just the you can say that the recap which we discussed in the last class, but it took us like half an hour because I just wanted to make sure that you understand these concepts, because these would be used very time and again in the coming chapters. So I just thought that it's worth spending additional half an hour on this just to make sure that you understand all these basic concepts. Now we would move on to the determination of that partial t upon partial y at y is equal to 0, which we discussed. So the let me share the I think my desktop screen with you so that I can use the whiteboard as well. So just a minute, give me 1 second. So I hope that you can see my lecture screen and we can see a very good picture of Atif in front of us. So that's good. So now we can move forward from here. Now, if I can show you the lectures, the whiteboard, I hope that you can see. So the formula for the calculation of H, that was H was equal to minus K of fluid into partial T by partial pi at y is equal to 0 divided by Ts minus T infinity. So now we can this is the main challenge here, that how to calculate this. So in order to calculate this, we need to find t as a function of xy. But in order to get to this, first we need to get uxy and vxy. Now you would be wondering why is the case that in order to get t, why we need u and v velocity. So the answer for that is the set of equations which govern the flow for the any fluid flow situation. So that set of equations is called Navier-Stokes equation. Okay. So you must have heard this name in the fluid mechanics. I hope. Just a minute, let me pen it a little bit just to show those equations here. Yes, anything? Because I thought that someone unmuted their mic. So if nothing to be asked, then we can continue with this. So here, first of all, in the Navier-Stokes equation, we have got continuity equation for the 2D steady state case. 2D steady state flow. Partial u by partial x plus partial v by partial y is equal to 0. And then we have got u momentum equation, या फिर उसको हम x momentum equation भी कहते हैं, that is equal to partial u by partial x plus u into partial sorry, I made a mistake here, plus v into partial u upon partial y, and then if we multiply it with rho on the left hand side, on the right hand side we can write dp by dx. Why it is minus? Because this is a closed term, you know, all know very well. Mu into, this is mu, let me write it again clearly. Okay, please don't be overwhelmed with these equations, because all these equations which I am writing it, you are not going to solve them numerically or anything. We need to get to some final destination, which is a functional form of this H calculation by using experiments. So that's but to in order to explain that how we reach up to that, so we need to know these equations. You don't need to memorize it, but you need to know that the procedure and the reasoning, that how these equations are manipulated to get to that functional form of H. So don't be afraid from these equations. So in this case, it would be u into partial v by this is now y momentum equation, v into partial v by partial y, and then minus dp by dp dy plus mu into partial square v upon partial x square plus partial square v upon partial y square. And then now these are the equations which gives you u, v, and p. Now, if we want to calculate also the temperature, then we need to write the energy equation. Rho Cp into u into partial T by partial x plus v into partial T by partial y equal to k into partial square T upon partial x square plus partial square T upon partial y square plus mu into psi plus q dot. Now q dot is the volumetric heat generation. Now psi is the dissipation rate, due to dissipation rate of energy due to the friction. That is, you can easily see that dissipation of energy when you rub your palms against each other. You kind of feel some heat being generated. So that is something that frictional energy is being converted into thermal energy, right? So in the fluid, due to the viscosity, some of the fluid energy is being converted into thermal energy. So that is that dissipation of energy. So uh, this psi is equal to partial u upon partial y plus partial p upon partial x square plus 2 into partial u upon partial x square plus partial p upon partial y square. Okay, so it is quite long relation. Now I think you would appreciate the effort which is these commercial software like ANSYS they do it for you, because you don't need to deal with all these equations. So all these equations are being actually solved at each grid point when you create the mesh and you apply the boundary conditions, and then uh, when you click that run button, simulation run button, then all these 4 5 equations for I am talking about only 2D steady state flow. So if it is 3D transient case, then we would have more equations and more variables. In that there would be time as well. So all these equations are being solved numerically on the back end of that fluent software, right? So that because I just wanted to tell you about the numerical solution of that, so that's why I give you the project, so that you can understand that. But at least now you know that for the 2D flow, all these equations are being solved if we want to calculate u velocity, v velocity, pressure, and temperature for a particular fluid flow heat transfer problem. Okay, so now because if we go up a little bit, we need partial t by partial y add by equal to 0. So it means that we only need this temperature information inside the boundary layer, right? So we don't need this information outside the boundary layer, which is the outer region. So it means that we need to solve uh, this equation inside the boundary layer. So it means that if I can apply if I can kind of simplify these equations by assuming some of the boundary layer assumptions, then it would be easier for me. So if I take a flow over a flat plate, so because the predominant direction of the flow is x, because we say u infinity. So I can the first assumption for the boundary layer. So let me write here boundary layer assumptions. So the first assumption which I can say that x, the velocity which is happening in x, which is u velocity, that is far greater than v velocity. V velocity is the wall normal velocity which is happening in the y direction. So this is the direction of x and this is the direction of y. So here we have got v velocity, here we have got u velocity. And then we have also seen that this is a boundary layer grow. So it means that the flow changes rapidly from this TS, which is the surface here, to the boundary layer thickness. So it means that I can also say that the second assumption I can take that partial u by partial y, it is far greater than partial u by partial x, and because we already sorry, and as since from the first assumption v, which is wall normal velocity, it is far less than the u velocity, so we can also say that partial u by partial y is also uh, very is far greater than partial v by partial x and partial v by partial y. Now, the important thing is partial v by partial y is also written on this side. While that, because the v velocity is very small as compared to u, so it means that this gradient would be very high. It means that the flow changes from zero velocity to the maximum free stream value in a very short time. So it means that that gradient is very high as compared to the other three gradients. Partial u by partial x, that velocity of in one layer would decrease rapidly, as I explained in the beginning in the answer to the query of Atif, I think. So the third boundary layer assumption is partial t by partial y. It is again it is greater than partial t by partial x. So these are the three assumptions which we say that for the flow on a boundary layer we would kind of take it, and we would have very less error because u velocity would be far greater than wall normal velocity, and the gradient in the y direction would be far greater than in the x direction, and as the gradient of v velocity, which is quite small. So if we apply it here, what will happen? Let me go back. So we leave the continuity equation because that only comes from conservation of mass. So we start with the momentum equation. So in this, the first term u is being multiplied with partial u by partial x. So you can easily see that a big numerical value is being multiplied with a smaller value which is not zero. So it means that we cannot ignore it. So it would remain, and then v into partial u upon partial y, it would also remain. While that okay, v is very small, but partial u by partial y is very large value. So it means that the left hand side would remain unchanged. And if we know that what is okay, dp by dx, that is also the pressure gradient, this remains. What will go in the last uh, that is a partial scale u upon partial x scale, because partial u by partial x is very small. So if we take the second gradient, it would be even smaller. So that's why partial scale u upon partial x scale would be neglected as compared to partial scale u upon partial y square. And now here for the y equation, because partial v by partial y is very small as compared to u, so we just say that this term is equal to 0, and then v into partial v by partial y, that is also 0, because a small quantity is being multiplied by even a smaller quantity, so we can say that is negligible. And then partial square v upon partial x square, that is also 0, and partial square v upon partial y square, they are also equal to 0. While there, because the v velocity is very small, and when we take its gradient, it would be even smaller. So we are only left with this. We say that in the boundary layer, partial p by partial y equal to 0. So it means that inside the boundary layer, the pressure only varies in x. In y, there is no variation of pressure. So that is kind of one conclusion of the boundary layer assumption. Now coming uh, towards the energy equation. For the energy equation, if we say that u into partial t by partial x, that would remain. Why is that? Because u is very large value, partial t by partial x, maybe it is not very large, but in the product it would have some significant value. And for second term, v, although v is small, but partial t by partial y is very large. So the left hand side would remain. On the right hand side, we would have the first term would go partial square t upon partial x square. Why is that? Because partial t by partial x is very small value as compared to partial t by partial y. So when we take the second derivative, it would be even smaller. So that's why we are ignoring this. Now, if we say that there is no volumetric heat generation there, so Q dot would be 0. In the phi term, we would have partial U by partial Y would stay there, but partial V by partial X, it would be 0. And then similarly, partial U by partial X would be 0, and then partial V by partial Y. These terms would be very small as compared to partial U by partial Y. So phi would remain only partial U by partial y square. So now if we write the equations which are left, so now the boundary layer equation, the above set of equations were Navier-Stokes equation. Now we are going to write the boundary layer equations which are being simplified due to those three assumptions. So now we can write rho into u into partial u by partial x plus v into partial u by partial y equal to minus dp by dx plus mu into partial square u upon partial y square. Right. So the second equation would be equal to partial p by partial y is equal to 0. That was the v momentum equation, and now the last bit is the is the temperature equation. So for the temperature, if I take you back there, if rho Cp being divided by the whole equation k upon rho Cp, that is equal to alpha thermal diffusivity, and then when mu is divided by rho, that is the nu, which is kinematic viscosity, right? And alpha is only partial u by partial y square, right? So uh, if I write that equation here after the simplification, I can write u, sorry, u into partial t by partial x plus v into partial t by partial y is equal to alpha which is k upon rho c partial square t upon partial y square plus nu upon cp, because it was mu upon rho, that is equal to nu, and then here I would have partial, not partial, u upon partial y square. So now those complex equations become virtually only the two equations. One is this, because we can kind of ignore this because this is not giving us anything, partial p by partial y. So that is kind of so we have to solve these two equations in order to get the value of u and then temperature. Now the problem here is that how to solve these equations. Now in order to solve these two equations, we have got two routes. One is either we solve them by using some mathematical analytic skills, and anything analytically we can solve it. So uh, that is done. That is called boundary layer equation solution. That was first done in 1907. Almost how much time? 113 years. So a PhD student whose name was Blossius. Sorry, I have written it wrong. Blossius. He gave the similarity solutions for boundary layer. So he changed these PDEs, partial differential equation, into ODEs by introducing some similarity functions. So we are not going into that detail for your peace of mind. So I am just telling you. So this Blossius was the PhD student of Prandtl, जिसका Prandtl number हमने पढ़ा ना अभी पीछे. He was the PhD student of that Prandtl. That was the He was the student of that, and he gave that solution in 1907. So those solutions are given in your book. you can go through that, and in we get a third order ODE, and we can solve it by using some iterative methods, Rangi Gutta or anything else. But we are not going in that direction. Instead, so this was the analytic solution. Okay. So, but because as in your FM course, you are also studying that experimental chapter, which is called what is it is called? What is the name of the chapter? Similitude, and then what is the exact name of the chapter number 7 you are going through at the moment?
Dimensionless analysis, sir.
Dimensionless analysis, modeling and similitude. ठीक है? Thank you for that. So dimensionless analysis, for that you must have heard the name of Buckingham Pi theorem. Have you heard this name up till now?
जी
Yes,
सर.
sir.
Okay,
Ji.
ji. So what do you do in this Buckingham Pi theorem? That first of all you write a functional form. Okay. Now in this case, u is dependent upon x, y, and if I write here, first of all we need to non-dimensionalize these equations, right? So if we non-dimensionalize these equations, then why we do the non-dimensional bit? Because for the Buckingham Pi theorem, you want to conduct the experiments on non-dimensional quantities so that you can have those results applicable to some other experiment facility as well, right? So that is the whole purpose. And the second purpose of non-dimensionalization is that we reduce the number of dependent variables. So it means that we need to we doing by performing the non-dimensionalization, we reduce the number of dependent variables and the number of experiments to be conducted, right? So in Buckingham Pi theorem, we write, first of all we kind of non-dimensionalize these two equations. So in order to apply the Buckingham Pi theorem, so if I show you the non-dimensionalization, so these are all the equations which I have shown you on the whiteboard, and then we applied those boundary layer assumptions, and once we apply the boundary layer assumption, we get to these three equations, 215 to 217. So partial p by partial y we don't need to solve because that is not going to give you anything. So it means that in essence we have to solve equation 215 and equation 217. Now, right. So as I told you that we can solve these PDs by using the similarity solution which was given by the Blossius. So we called it Blossius solution in 1907. So he converted these PDs into ODs by using similarity functions. So but that is an analytic way of doing things, so we are more towards the experimental thing or numerical thing. So that's why we would go to the second route, which is first of all we need to non-dimensionalize equation 215 and equation 217. So in order to non-dimensionalize it, we need to define some dimensionless variables as you do it for the pi terms as well in your chapter number 7. So here we can non-dimensionalize x with x star. So we non-dimensionalize it by using the length of that flat plate. So the length of the flat plate, which is L in this case, so we are using that to non-dimensionalize the length variable, and then in order to non-dimensionalize velocity variable, we are using u infinity, which is the free stream velocity. So that makes sense for the external flow over a boundary layer. So we are using that, and then because that is the characteristic length here, characteristic length is L and characteristic velocity is u infinity. Similarly, for the pressure, we can use P upon rho u infinity square, and then for the temperature, we can use T star, which is T minus Ts divided by T infinity minus Ts, right? So these are the four variables which we are using to non-dimensionalize the equation which are shown in equation 215 and 217. You don't need to memorize anything, but you need to know the procedure that how we are moving along. So at the moment you don't need to cram anything. Only you need to do is to know the process that we are following to get to our that booking pi terms, that how to get to those pi terms. So once we apply this non-dimensionalization on equation 215 and 217, we can get to these equations. Now here the variable with static, that are the non-dimensional variables which are defined here in these four lines, right? So now if we kind of let me, what we need to do here, we can have a snap tool, I think. Snap, snapping tool. Let's see that how can we use it. Okay, so let me snap it. So hopefully I would be able to copy it, and then let me take it back to the whiteboard. Let me pan it a little bit. So let me paste it here. I think you would be able to see it. So okay, so these are the two equations, right? So if you see that in the first equation we want to determine u. So as you do in the Buckingham pi theorem, first of all you write the functional form, that uh, the dependent variable is written in terms of independent variable. So here if I write that functional form, so for the u I would only write the functional form, but for the temperature we would do a little bit more work on that. So if I write the functional form, u star is function of x, y, Reynolds number, and dpy/dx. So it means that if we want to get to know the variation of u with x, y, with these independent variables, we need to run four sets of experiments. So then we would be able to get the functional form of u in terms of x, y, Reynolds number, and dp/dx. For the temperature, we have got x, y, Reynolds number, Prandtl number, and we only these four bits. Now we wouldn't be talking much about this velocity, because that you would get to know in FM2, because from here we can define CF in terms of u, which you would surely come across in your FM2 course. So we are focusing on the second bit, which is this, right? So now if you remember from your from the H definition which we studied in the beginning of this lecture, that was equal to minus k into partial t by partial y at y is equal to 0 divided by ts minus t infinity. Now we need to get t star here somehow, to see that how we can write it in terms of h. So because we have written all our equation
सर
in
टी
terms of,
इन्फिनिटी आएगा
oh sorry,
सर.
thank you for the correction, thank you. That is just a typo mistake. Thank you, Shariz. I think Shariz or Asif. I can't distinguish between your voices, but one of you. Okay, ji, thank you. So now I need to get T star here somehow because we have written it in terms of T star, which is non-dimensional time. So if I go back and see that how I did the non-dimensionalization, T star is equal to T minus Ts divided by T infinity minus Ts. If you remember this, T minus Ts. So if I write here, T star is equal to T minus Ts and Ts minus T infinity. So from here I can write T is equal to T star into Ts minus T infinity plus Ts. I think that we are good enough to do this, all of us.
सर टी इन्फिनिटी माइनस टी एस है सर.
Oh, yes. Thank you. Again, thank you. I asked you to remember it, but I, I didn't give it much thought when I was writing it. Thank you for the correction again. Now here it would be T infinity minus Ts. So let me do the correction. T infinity minus Ts. Right. So now if I put it here in this formula, so if I write a partial t by partial y at y is equal to 0, I can write it partial t star upon partial y into t infinity minus ts, right, plus partial ts by partial y at y is equal to 0, right. So this term would be equal, the second term would be equal to 0. Why is that? Because partial Ts is a constant value, so it means that it is not going to vary with y. The only thing which is going to vary, that is t, which is a function of y. Which is, here it is t star, or here it is also y, function of y, and this is also function of y. So it means that they are going to vary. So if I put this value here, so if I put it here, what I would get, h is equal to minus k into partial t star upon partial y star at y is equal to 0 into t infinity minus ts divided by, sorry, maybe it was not the best line I have drawn, divided by ts minus t infinity. Now if I take this minus inside, so if I remove it, so then it would become Ts minus T infinity. So we have also got it in the numerator as well as denominator. So we can just cancel it, right? And then, okay, one thing I have missed here, maybe you haven't noticed, that I have written partial t by partial y here. So when I write here partial y, when I need to put y star here, then I need to multiply it with L also, right? Because y star is basically equal to y upon yl, right? So when I put partial t star, that is okay. But when I put partial y star, then I need to also because I am dividing it by a length here, then I need to also multiply it here. So here it would be L as well, which is being not here. Sorry, it would be in the denominator. Do you understand that from where this length came? Because uh, if I take you back here, when I take partial t by partial y, but I need to write partial t star divided by partial y star. So in order to put y star, I need to divide y by L to get y star. But when I am doing the division, then I also need the multiplication in the denominator. So that denominator bit would come here. So now if I see, if I want to write partial t by partial y star,
सर आपने पहले टी इन्फिनिटी माइनस टी एस लिखा है और फिर बाद में आपने टी एस माइनस इन्फिनिटी लिखा है
जी बिल्कुल लिखा है.
क्या
अच्छा, मैं दोबारा एक्सप्लेन कर देता हूँ. बिफोर आई राइट दिस आई गो बैक देयर. Actually, there was minus here, and it was written like t infinity minus ts. ठीक है, Vinahil? Do you understand? Now, if I
जी
take this minus inside, then it would become. It means that if I, because if you go a little bit back, if I take you here, it is minus. ठीक है, तो that minus would also come here. तो उसको अगर मैं अंदर ये ब्रैकेट के अंदर ले जाता हूँ तो ये वाली चीज मेरे पास फिर आई थिंक दैट यू हैव गॉट द पॉइंट.
यस सर
Okay, so this bit would come. Let me write it again. Ts minus T infinity. In the beginning, it was T infinity minus Ts, but because there were minus, so when I considered that, so it became Ts minus T infinity, so it kind of cancelled out. So then I talked about the introduction of y star. So in order to get y star here, I need y divided by L. So it means that I also need the multiplication on the denominator side with this length of the that flat plate. So that came here. So now if we try to write a non-dimensional gradient of partial t by partial y at uh, y is equal to 0, then that would be equal to HL upon K. So what is this HL upon K? Because this is K fluid. What is HL upon K?
Nusselt number, sir.
Nusselt number. Nusselt number. Right. So excellent. So now if we go rewrite the functional form where we have, if I show you that functional form, just for the clarity, T T star is function of x star y star re L REL mean that here the length where we are using that is the length of the flat plate and Prandtl number. So if I write it again here, just for the uh, convenience of seeing things, why don't we need any static here, Reynolds number and Prandtl number? Anyone? Just
Sir,
to
वो
see.
पहले ही dimensionless है.
Yes. Okay. So it means that they are basically already a pi term. So here this x star is a pi term, y star is a pi term, t star is kind of a pi term, and so now if we take y star from, because now we can introduce Nusselt number here. How is that? If we write it partial t by partial y, which is equal to Nusselt number. So Nusselt number now function of x star REL and Prandtl number. Where does this y star went? It is on the left hand side, because if we have that thing that is equal to Nusselt number, which is also equal to HL upon K. Now it means that if we want to know Nusselt number as a function of x along that flat plate, if I redraw it here somewhere, let me. Now, what does this mean, this relation? If I, here it means that Nusselt number is a function of x. So it means that we can also determine Nusselt number at this location at point 1, point 2, point 3, because it is a function of x. So we can determine it as a function of x star, right? So what if I want to calculate Nusselt number on the whole plate? So in that, what I need to do that Nusselt number that would be equal to 1 upon L into 0 to x Nusselt number x star into dx star, right? So if I take the integral, I would be able to get Nusselt number which is applicable to this entire plate. Then for that case, I would have Nusselt number only function of Nusselt number only function of REL into Prandtl number. So this is the functional form of temperature. Now, what does it tell you? That it is very easy to determine H. If we want to determine H here, HL upon K आना चाहिए जहाँ पे HL upon K D पता नहीं मैंने क्यों लिख दिया HL upon K आना चाहिए तो ये हमें ये जो functional form है it is telling us that if we want to determine H which can be determined from the Nusselt number then we need to conduct experiments, two sets of experiments in which we would have Nusselt number as a function of this Reynolds number and Prandtl number. So once we get that functionality by conducting those experiments, from there we can always calculate H by putting the value of this capital L, which is the length of the flat plate, and the thermal conductivity of the fluid. So it means that starting from the Navier-Stokes equation, then we applied the boundary layer assumptions, then we non-dimensionalized to write it in terms of pi terms, then we introduced Nusselt number. So it means that now all that equations reduces to a very simplified functional form in which we can determine H by only conducting experiments or writing the relation of Nusselt number in terms of Reynolds number and Prandtl number. So for the next two chapters, which are the first of all, we would be discussing, I think, external flows. So before that, let me show you that on the slides, which I have just explained. If you can see these two relations, then if you ignore this fluid flow thing, because that is something you are going to do in your FM2 course. So because in the book it was written, so I just wrote it here. So if you see this equation, so I have just ignored the dp by dx because that is given to us. So in that case, x, y, Reynolds number and Prandtl number, and then you can see that we discussed Nusselt number as a function of x star, Reynolds number, and Prandtl number, and then we can write the average Nusselt number as a function of Reynolds number and Prandtl number, right? So in chapter number 7 and chapter number 8, we would be writing Nusselt number only in terms of Reynolds number and Prandtl number if we are talking about average Reynolds number. So if we are talking about local Reynolds number, which is function of x, then there would be an additional parameter of x. So we would be talking about empirical correlation. So let me go back to the, so what we would be doing in this in the next two chapters, apart from the for the laminar cases, for the laminar flow, For the laminar flow, like Blossius solutions are available. Blossius boundary layer solutions are available. But for the turbulent flow, we cannot have Blossius solution because in turbulence there are many other parameters and we cannot apply those simplifications. So for the turbulent flow, we would have empirical correlations which are determined by conduct of experiments. So scientists have conducted those experiments and given us the Nusselt number correlations for different kinds of flows. So what kind of flows we are talking about here in chapter number 7? We would have external flows, and in chapter number 8 we have internal flows. Any example of external flow? Any example? Flow over car, ship, ship, aeroplane, buildings, and what else? Flow over a cylinder, cricket ball, which is a sphere, then tube bank. There are many cylindrical objects uh, which are uh, arranged in a collection. So that is a tube bank. For the internal flow, we have got pipe flow, duct flow, flow inside uh, human veins, inside human lungs, that are all come into the category of internal flows. Okay? So in chapter number 7 we would be discussing external flows, and in chapter number 8 we would be discussing internal flows. So the same two chapters for the fluid flow analysis you would be studying in FM2, right? So at the moment you are on chapter number 7. After that, that is chapter number 8, which is internal flows. In that you would be discussing about major and minor losses, and then external flows, that is flow over sphere, cylinder, and these things, and flat plate boundary layer concept, which I have already given you, but not in greater detail because that is not the purpose of heat and mass transfer. So we would be focusing more on to the heat transfer problem rather than fluid flow problem. So major and minor losses you would be discussing in your FM2 courses. Okay, internal flows, right? So okay, now this was chapter number 6. So we have derived the functional form. So we won't be going any further, but just a little question: what is a drag force? What is drag force? Anyone?
It is the force that resists motion.
It is a force exerted by a fluid on a body, and equal and opposite force is being exerted by the body on that fluid. So that is the drag force, and it is in the direction of flow. That is very important. Direction of flow. Okay, ji. What is lift force?
सर जो फ्लूइड परपेंडिकुलर है
हाँ जी,
body
फोर्स
है।
exerted by the fluid on a body in the perpendicular direction। तो ये जो लिखा हुआ है इसमें सिर्फ एक चीज ऐड कर लें, यानी चेंज कर लें, in the perpendicular direction। And that is the force which keeps aeroplane keep flying. Due to that difference in pressure at the lower side of that aerofoil we would have high pressure, and on the upper side we would have low pressure. So that difference in pressure creates an upward force which is lift force, right? लिफ्ट फोर्स में क्या होता है कि जो डाउन साइड होती है ऑब्जेक्ट की, वहां पे हाई प्रेशर होता है, और जो अप साइड होती है उस पे लो प्रेशर होता है। तो ये जो डिफरेंस इन प्रेशर होता है, दिस गिव्स राइज टू एन अपवर्ड फोर्स व्हिच इज कॉल्ड द लिफ्ट फोर्स। ओके, नाउ इन ड्रैग फोर्स we have got two components. Drag force, two components. One is called pressure drag.
ब्रेक दे दें।
ब्रेक क्या देनी है, बस खत्म कर रहे हैं। विद इन 5 मिनट्स वी वुड बी कंक्लूडिंग, दैट्स इट। मैं आपको सिर्फ एक ये दो तीन बातें बता के वी वुड कॉल इट अ डे। नाउ व्हाट इज प्रेशर ड्रैग हियर? इफ वी हैव गॉट अ ब्लंट बॉडी, ठीक है, ब्लंट बॉडी क्या होती है? जिसका जो एरिया होता है, जो कि किसी भी फ्लो में, जैसे ये एक वॉल है और इसके ऊपर से अगर फ्लो यहाँ से आ रहा है, क्या होगा कि ये जो मिड वाली है ये यहाँ पे आएगी, यहाँ पे स्टेग्नेशन पॉइंट होगा, और बाकी सारी यहाँ पे कैसे फ्लो करेगा ना, और यहाँ पे फ्लो सेपरेशन होगी, और उसके बाद वो यहाँ पे जाके ये मीट। इस रीजन को आप कहते हैं वेग रीजन, जो कि डाउन स्ट्रीम ऑफ बॉडी होती है, और उसमें जो वेलोसिटी होती है इट इज डिफरेंट फ्रॉम द फ्री स्ट्रीम वेलोसिटी। ठीक है, ये वाला जो रीजन होता है, दिस इज हाई प्रेशर रीजन, and this is the region where the flow separation happens, that is low pressure region. Now this difference in pressure creates a pressure drag force on a blunt body. So this is only for a blunt body, या फिर इसको ब्लफ बॉडी भी कह देते हैं। ठीक है, दूसरी टाइप ऑफ ड्रैग होता है जो कि लास्ट हमारा डिस्कशन पॉइंट है फॉर टुडे, उसको कहते हैं हम फ्रिक्शन, फ्रिक्शन ड्रैग, या फिर उसके बिगनिंग में हम स्किन फ्रिक्शन कहते हैं, स्किन फ्रिक्शन ड्रैग कहते हैं। ठीक है, वो क्या होता है? लेट मी एक्सप्लेन इट क्विकली एंड देन वी वुड कॉल इट अ डे। उसमें क्या होता है कि ये जो आपकी बॉडी है, ये वॉल है, अगर इसको हम 90 डिग्री पे देखें, तो ये now the flow would come here on both sides and there would be some kind of boundary layer है, जो कि अभी हमने डिस्कस की है कि वो आएगा, and then we would have greater contact of fluid with this surface area। यहाँ पे जो सरफेस एरिया हो रहा था वो सिर्फ यहाँ पे हो रहा था, ये वाली जगह थी ना जहाँ पे कांटेक्ट हो रहा था, ये जो मैंने रेड किया है। लेकिन यहाँ पे कांटेक्ट कहाँ पे हो रहा है? इस सारी सरफेस के ऊपर हो रहा है, यहाँ पे भी हो रहा है और इस सरफेस के ऊपर भी हो रहा है, लोअर और अपवर्ड। और ये जो मैंने ड्रॉ की है ये बाउंड्री लेयर है यहाँ पे, जो कि दोनों साइड पे ड्रॉ होगी। अच्छा, अब हम इसे कहते हैं कि इसके अंदर प्रेशर ड्रैग के अंदर वो जो ड्रैग फोर्स थी ड्यू टू डिफरेंस इन प्रेशर थी। यहाँ पे जो ड्रैग फोर्स है दैट इज ड्यू टू shear stress which is at the surface of the surface of the surface that is basically tau wall, जिसको हम कहते हैं mu into partial u by partial y at y is equal to 0. So in skin friction drag, the major component for the drag production is the shear stress, because surface area available for the fluid contact is more. So this shear stress plays a major role in that. But in the pressure drag, the difference in pressure is the plays the major role. So these were the two components which I wanted to tell you. So if there is any question you can ask. Otherwise, after downloading that attendance, uh, I would be happy to conclude this lecture. Okay, ji. So I have downloaded the attendance. So in the next week, you would have a quiz from chapter number 4 and 5. ठीक है, नेक्स्ट वीक में आपका चैप्टर नंबर 4 जो कि टू डिमेंशनल स्टेडी स्टेट कंडक्शन थी और ट्रांजिएंट कंडक्शन थी, तो उससे हम एक टेस्ट आपका क्विज ले लेंगे। ठीक है, सो बी प्रिपेयर्ड फॉर दैट। डू यू अंडरस्टैंड दिस?
Okay, sir.
So in next week, please prepare chapter number 4 and chapter number 5. ठीक है, and we would have a quiz in Wednesday class, 1 hour class next week. Okay ji. If there is no query, then we can have